In this lecture, we're going to be introduced to the idea of diastereomers. We're going to look at these in a lot more detail in the next module, but I want us to get warmed up thinking about diastereomers, how to identify them, and what their kind of impact is on this whole framework of stereoisomers. So we have our notes in front of us now. Let's just do a quick review about diastereomers. So diastereomers are stereoisomers that are not mirror images. So not mirror images is key, but also is key is that these the kind of di prefix here, because that reminds us that we typically have diastereomers when we have two or more stereocenters. Okay, two or more stereocenters. And in fact, we can determine the total number of stereoisomers for a molecule. So that's a fairly easy equation, and it's 2 to the n equals the number of stereoisomers for a chiral molecule. Now there is a caveat to this, but we'll get to that in the next module. No sense in worrying about it now. 2 to the n, where n is the number of stereocenters. Okay, so if you've got 2 stereocenters, then 2 to the power 2 equals 4 total stereoisomers. Now let's look at an example of this, 2 stereoisomers. We should have, 2 stereocenters. We should have 4 stereoisomers total. So let's say that I have this molecule, and I'm tasked with draw all stereoisomers. So I want to draw all stereoisomers of this molecule. Now what I first want to recognize is that I have 2 stereocenters in this molecule. The molecule doesn't have any wedges or dashes, so we need to add those as we draw our stereoisomers. And we expect 4 stereoisomers for this particular molecule. These are just actually permutations of the wedge or dash at every stereocenter. That is to say, I could have an example where I've got a wedge combination. I could have an example where I've got a wedge dash combination, then a dash wedge combination, and then a dash dash combination. So that's all that equation is telling us. It's just like a little permutation question where it says if all of the stereocenters could be either wedge or dash, can you then predict the total number of combinations of wedge and dash that you can have? And that's all a stereoisomer is. So this first molecule is not a stereoisomer. And that's because we didn't actually depict the arrangement in 3 dimensions. We just depicted the connectivity. The arrangement in 3 dimensions comes from the wedges and dashes. So we have our 4 structures. What I want to do now is I want to label each pair of structures as enantiomers or diastereomers. Okay, this is a question I actually need us to be able to solve. I want to give you a molecule with all straight lines, no wedges and dashes. I want you to draw all of the stereoisomers. And then pair them up. And for every pair, we're going to then designate that pair as being a pair of enantiomers, diastereomers, and that sort of thing. Okay, so let's go ahead. I'm going to redraw, just because I had to go on a separate page of notes. I'm going to redraw the stereoisomers. We're going to go OH, 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 BR, 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 BR. We have our 4 stereoisomers, the 4 permutations that we could predict from the equation. Now what I want to do is I'm going to assign A, B, C, and D. This is going to make things so much easier because as I draw the pairs, now I can just reference this labeling scheme. So what I want to do is I want to do A versus B, A versus C, A versus D. Now I've compared A to everything. And I'm going to write either a D or an E, enantiomer versus diastereomer. But I could still do B versus C, right? And B versus D. And I could still do C versus D. And now I've got all 6 kind of combinations of comparison points for these 2 structures. So what I want to do is write an E equals enantiomer, and then D equals diastereomer. So that's what's going to go to the right of the arrows in every case. So with enantiomers, we flip everything. So I mentioned that in the last few lectures as we were talking about enantiomers. I said if we kept the orientation of the molecules the same, in this case we're going to have, you know, OH on the left side in every case and BR on the right side and down in every case. Okay, the orientation is the same. So if I keep the orientation the same, I can draw enantiomers by flipping all of the wedges and dashes around. Now in the enantiomers that we were looking at previously, what we saw were molecules that only had 1 stereocenter. Here we have 2 stereocenters shown with the wedges and dashes. And I'm not considering the hydrogens pointing out, but we know that they're there to give us that 4th different unit at each of the stereocenters or chiral carbons. Okay, so with enantiomers, we flip everything. And with diastereomers, we flip some things. We flip some of the wedges and dashes. Some implies something got flipped, but not everything got flipped. Okay, so A versus B. Let's look at A versus B. In this case, when we compare A versus B, the only thing that changes is that the BR wedge flipped to a dash. And as a result, I would say between A and B, some things flip, but not everything. So those 2 molecules are diastereomers of each other. Now A versus C is similar. In this case, the BR has remained the same, but the OH is flipped. Some things flip, but not everything. And as a result, they are diastereomers. A versus D, now everything is flipped. All of our wedges from the starting structure flipped to dashes while we kept the orientation the same. So that's going to be labeled as an enantiomer. Now B versus C, ooh, this is interesting. We actually have another enantiomer pair. The OH is flipped, the BR is flipped, but they've like flipped in opposite directions, right? Because we started differently in this case. And so B versus C, that is an enantiomeric pair. B versus D is diastereomeric because the OH flips only. And then C versus D is also a pair of diastereomers. So again, what I want us to be able to do is for any molecule, I want us to draw all possible stereoisomers, which is a permutation of wedges and dashes. Then I want us to kind of label those and then pair them up, A versus B, C, D, that sort of thing. And then I want to label each pair as enantiomers or diastereomers. So why is it important to be able to do this? Well, it's because we've talked about all the special things about enantiomers. We said how they have subtle differences. Sometimes they're the same in very weird ways, like melting point and boiling point. These are different molecules. Why do they melt and boil at the same temperature. But their interaction with chiral systems, and there's so many chiral systems around us, is different, and that leads to sometimes catastrophic effects if we're not careful. Diastereomers are completely different in every way except for what makes them isomers, which is compositions and connectivity. So recall that diastereomers, okay, these differ in every way except composition, because then they wouldn't be isomers, and connectivity, because if they differed in connectivity, they would be not stereoisomers, but constitutional isomers. The other thing I'll just mention is that the optical rotation for diastereomers of one diastereomer is completely different than another, okay? So the optical rotations are not specific rotations, whatever, have no relationship. You can't say they're opposite. You can't say they're opposite sign. You can't even take a guess. If you look at one by itself, one molecule, and you'd be like, oh, its optical rotation is plus 50. When you look at a diastereomer, you can make no guesses. It could be plus 50. It could be plus 48. It could be minus 27.2. We don't know, okay? So you just can't make any connections. The only thing that's the same about diastereomers is their connectivity and composition, but everything else is different. And the reason why it's different is because some of the stereocenters have changed their three-dimensional orientation, but not all of them. By doing that, they're no longer mirror images of each other. So it's the enantiomers that are very special. It's the diastereomers that are just a little bit more complicated because they have more stereoisomers. Okay. I think, barring me realizing there's something dramatic that we've overlooked, I think this is a good stopping place for Module 3. So I think that's where we'll end for Module 3. Again, I guess if I see something in the notes that I forgot to mention, I'll obviously throw it up as like a lecture 59 or something, okay?